Hello class, and thank you for watching the second part to the rational to the zeros of polynomial functions. Today we're going to now identify the zeros of polynomial functions using the rational zero theorem. Now it states here that if a polynomial function, again in the format, has real coefficients, so all of these numbers are real numbers, then every rational zero of f of this polynomial is going to be in the following form, in the format of p divided by q, where p is going to be, as you see right here, the factors of this last number of the constants, and q are the factors of your leading coefficients. So this number right here in the front. And of course, p and q have no common factor other than 1. Now, to use this theorem, we're going to list the integers that are factors of the constant and the leading coefficient. Then we list all the possible rational zeros by dividing each of the constants by each factor of the constant by each factor of the leading coefficient. So let's take a look at an example of this. So let's look at example 4a. So here in this example, we want to create a list of all possible rational zeros. So we begin by looking at the constant, this number right here, and finding all of the factors of 72, which are going to be the numbers that divide 72 without remainder. So going in order, starting with the smallest one, 72 can obviously be divided by 1. And of course, it could also be divided by -1. So we're going to consider both positive and -1. 72 can be divided by +2, but also -2, positive and -3. 72 can also be divided by 4. 72 cannot be divided by 5 because that's going to give you a decimal value, but 72 can be divided by 6. 72 can be divided by 8. And of course, it could also be divided by 9, since 8 times 9 is equal to 72. And the other values are now going to be the following. 72 can be divided by 12. So it's a pretty long list here. 18, 24. Let me continue the list down here. Where was I? 24, 36. And of course, itself. 72 can be divided by itself. So here is a long list of possible numbers that could divide 72. Now let's look at the leading coefficient. Our leading coefficient on this example is 1. So this one is an easy one. The factors of 1, the numbers that divide 1, again, aka factors, it's only going to be itself. So 1 could be divided by +1 and 1 could be divided by -1. Now, to come up with the list of possible rational zeros, all we're going to do is simply get this list of numbers up here, so those numbers there, and divide it by that value right here, by this one identical value. And because it's 1, well, all of these numbers divided by 1 is going to give me the same list. So let me just highlight this so I don't have to rewrite this. Let me copy it, duplicate it, and this right here is going to be our list of possible rational zeros. So that means that this polynomial, x to the third power minus 18x squared plus 89x minus 72, this should be crossing the x-axis at one of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24 places. So we have 24 possible places that the graph can cross the x-axis. Let's see. Let's graph this on decimals and let's see if that correlates to those numbers here. Okay, so here I have the function again. I already graphed it on there. And let's see where we cross the x-axis. We cross the x-axis at 1. We have an x-intercept at 8. And we have an x-intercept at 9. Let's see if those numbers are going to be found on the list. We see positive 1 right here, obviously at the very beginning of our list, positive 1. We have positive 9. Yep, look, positive 9 is on the list, and so is positive 8. Look at that. All of those three places that the graph crosses the x-axis can be found on this list. So we use this list in order to identify possible rational solutions, and as you'll see in the next a couple of examples after this, we use this list in order to be able to identify where the graph is going to cross the x-axis and where the possible solutions are going to be in this one. But again, it correlates perfectly to the concept of the possible rational zero. So the rational zero theorem, given again that all of these numbers are real numbers, then the rational zeros, the whole numbers or decimal values that are going to cross the x-axis, again, rational numbers, they'll be written as fractions, is going to be again somewhere in this list right there. So let's look at that second example. Let's now look at example 4b. So again, let's practice again how to regenerate this list. So here, for this example, we're going to start again with the last number, 18. Do not worry about it being negative. We just care about what numbers divide 18. And in every situation, there's two possible choices, the positive and negative value of the number. Starting off with 1, obviously 1 divides everything. 18 can be divided by 2 because it's an even number. 18 cannot be divided by, oh no, I'm sorry, it can be divided by 3. 18 divided by 3 is equal to 6, so 3 is a factor. 18 cannot be divided by 4 because that gives you a decimal, nor can it be divided by 5, but we can divide it by 6. 18 divided by 6 is equal to 3. So that means that the next number in the list is going to be the number that divides to give you 2. Well, that's going to be a total of 9. And the next number after that will be the number that 18 can be divided to give you the answer of 1. That would be 18. And of course, positive and negative values. So there is our list right there of the factors of our constant. Now our leading coefficient yet again is 1, so that makes that part easy. So that means that the list of possible rational zeros will be positive or negative 1, positive or negative 2, 3, 6, 9, and 18. So let's look at the graph of this thing and see where it's actually crossing the x-axis and verify that our answer can be found in this list here. So in this list. So here I have our graph, our polynomial function. Let's click on those zeros. And here are our values. We have 1, 2, and 9. And there we have them. Look, how cool is that? Those numbers are on the list. Positive 1 is on the list, positive 2 on the list, and positive 9 on the list. Excellent. So we found again that our list does in fact have where the graph is going to possibly cross the x-axis. All these other options, obviously, it's not going to cross the x-axis at all of those values, but where it does cross, those numbers again are found in our list of possible rational values. So let me scoot this over right here, okay? So there we find those numbers again, our x-intercepts to be on this list here. How cool is that? So now let's look at this example. In this example right here, our leading coefficient is the value of 3. So that's different. And our constant is going to be 28. So let's start with the constant first, so 28. And let's figure out the factors of 28. Remember, identifying the factors is essentially just finding what numbers divide to give you an integer as an answer. So a quotient of an integer. So 28 could be divided by 1 with no remainder. 28 could be divided by 2 with no remainder. It cannot be divided by 3. It could be divided by 4 with no remainder. We cannot divide by 5, nor can we divide by 6, but we can divide, by 7. I was going to say no to 7, but yes, 7 is a factor of 28. And since 28 divided by 7 gives you 4, then that means that the next number is going to be the number that the answer, the quotient, is going to be 2. So that's going to be 14. And the number after that will be the value that divides to give you an answer of 1, which is going to be 28. So the list of factors of 28 are here. Now, On the previous examples, we had a factor only of the values of 1. Here we have a prime number of 3. So the list isn't going to be that long. The only numbers that give me the value of 3 are going to be 1 and 3 because 3 is prime. Now, in this situation here, our list of possible rational zeros has to divide every single one of these values by those quantities there, okay? So let's start by dividing all of these numbers first by the value of 1, which is going to be easy because dividing all of those numbers by 1 is going to keep those values the same. So I'm just going to simply duplicate this list. So there's that part of the list. Now what we want to do is divide all of these numbers by that second value. So we want to divide them all by 3. So 1 divided by 3 is going to create the ratio of 1 over 3. 2 divided by 3 is the ratio of 2 over 3. And then 4 will divide 7 by 3. Our next number is 14. And our last number is 28. Now these numbers cannot have a common factor, meaning that if I have to reduce anything, if anything is reducible, there's a common factor, I have to reduce that out and write this fraction in a simpler form. But there is our list of possible rational zeros. So let's look at the graph of this function and see if though it's true that our x-intercepts can be found in these two lists here, in these two rows. So here's the graph of our function, of our polynomial function, and let's click on these x-intercepts. Okay, so we obviously see 4. 4 is on that list. Positive 4 is right here, so is positive 7. But we have this fraction of this decimal value of 0.333333. Well, that's the fraction of 1 over 3, which again is on that list. So if I convert that into a decimal, into a fraction using decimals, there it is. Okay, I get the fraction of 1 over 3. So there you have it. Again, our list provides possible places where our graph is going to cross the x-axis, and when we graph it and find the exact values, we can clearly see that those x-intercepts, again, those 3 numbers are somewhere in these 2 rows on this list. How cool is that? So let's practice one more example of this technique. So here our constant is 4, and 4 doesn't have a long list of factors, only 1, 2, and 4. And again, 3 is a prime number, so from the previous example, we know that that's only going to be 1 and 3. So our list of possible, again, that's the key word there, possible rational zeros will be all of these values divided by 1, which is just going to be that list. It's not too many, so I don't have to copy and paste. And then all of those numbers divided by 3, which again is not going to be a long list. It'll be, let me write it underneath. It'll be 1 over 3, 2 over 3, and then 4 divided by 3. So again, not a very long list of possible rational zeros. Let me erase this, okay? So now let's look at decimals and let's again verify that our zeros are on this list. So here again I have the function for f graphed on decimals, and let's look at where it crosses the x-axis. We cross the x-axis at 0.6667 at 1 over and 1 0, I'm sorry, 1 0, not 1 over, but 1 0, and then that's 2 0. Well, 2 and 0 are easy to find. I'm sorry, 1 and 0 and 2 0 are easy to find. That's right there. So yes, those numbers are still found on that list. And the last number is that decimal value of 0.6 with the repeating value of 6. So 0.6, when I first convert it into a fraction, gives me this fraction of 3 over 5, but that's not the appropriate one because obviously 3 over 5 is there. The 6 keeps on repeating, so I need to repeat the 6 until you see the fraction goes away and then reappears. So whenever you have a repeating decimal, to use decimal to convert this into a fraction, you have to repeat that decimal value over until the conversion disappears and then reappears again. So 2 over 3, that is actually on the list. 2 over 3 and positive 2 over 3 is on the list, like I said, and voila. So cool, very, very cool that, again, this theorem in fact does work. It gives me a list of possible places that the graph is going to cross the x-axis. So let's look at this, and let's now apply this concept since we know that this list generates, again, the places where the graph is going to cross the x-axis. Let's use this possible list to find out where the rational zeros to a polynomial equation are, and use synthetic division to find the other ones, the remaining ones. So let's turn the page to the other side. Now, let's apply again this concept to finding the list of possible rational zeros to actually finding the rational zeros without having a graph. Now, to find the first rational zero, we use again that list of possible rational zeros, and then by trial and error, a trial and error process involving synthetic division or synthetic substitution, we can identify which of those is going to be a factor. Now recall that f of x is divided by x minus c, and the remainder is 0, means that c is going to not be a factor. That's not the right word here. It's going to be a 0, meaning that when I plug in the function of the value of c into the function of f, I should get the number 0 as a result. Now, after identifying that first rational zero, we can use the result to that synthetic division to factor the original polynomial. Then setting up each factor equal to 0 identifies any additional zeros as a result. Now, let's review the type of zeros. Before we look at an example, let's review the type of zeros that exist. Now, there's 3 types of zeros that exist. We have our rational zeros. We have our irrational ones. And then the complex zeros. Our rational zeros are any function, again, any number that's going to be in the form of a fraction. Like whole numbers are in the form of fractions. For example, this one right here, x plus 3 is a factor. So that would mean that x minus 3 from both sides, saying that x equals to negative 3, is going to be one of our zeros. So substituting a negative 3 into this parentheses will make the entire thing equal to 0. And this is an example of a rational zero because negative 3 is a rational number. It's a fraction. Negative 3 divided by 1. The other one is a little bit more obvious as a rational value because 2x minus 1, when we set that equal to 0, we find that the value of x will equal to positive 1 divided by 2. That's more obvious that it's a ratio of 2 values because 1 over 2, 1 to 2 is a ratio. But again, whole numbers are also considered rational as ratios because those values are technically written over the value of 1. But since we're writing it over the value of 1, hence why we only have the numerator portion of that ratio. Now, the second type of zeros that exist are irrational. That's the result of having to use the quadratic formula, and we end up with the square root of some non-perfect square. Like right here, x will equal to a negative square root of 2 or a positive square root of 2. And we're going to notice about these numbers here is that these numbers, along with the complex numbers, they always come in pairs. They always come in a pair where the radical part is always going to be either subtracted or added to either a whole number, like in this case the number would be 0, or some other whole number again like 5, 7, 12, whatever. But you're always going to end up coming again having a pair of radicals where one is negative and the other one is going to be plus, being added to some value here. And like I said, that same thing is going to be true with our complex numbers. So for this right here to become 0, we would have to get the opposite of this complex number there. So x will equal to a positive 4 minus 5i. And for the last parentheses, that would have to be a positive 4 plus 5i. And as you notice, they also come in opposite pairs. The imaginary part is a negative 5 and a positive 5i. So again, we have our whole number there, our rational or real, in this case, real part there, and then our zeros come in conjugate pairs where one is going to be minus and the other one's going to be positive. Okay, so let's finally put again the rational zero theorem to test. So here, I want to start by first figuring out and creating a list of possible rational zeros, which would begin by getting the factors, and move this down, by getting the factors of this last number here, which is 6. So positive and negative 1, positive and negative 2, 3, and 6, and dividing them by the leading coefficient, which is going to be 1. And since it's 1, well, dividing all of those numbers by 1, because there's only one possible factor of 1, is going to give me this one list, this list again. So let me just copy and paste that right there. And you're going to notice again, you'll notice quite quickly that anytime that the leading coefficient is 1, then our list of possible rational zeros is simply going to be the factors of our constant, because we're dividing again all of those values only by the number 1, so we're not going to get anything else other than that list right there. Now that we have the list, again, this is possibly, again, of these 8 numbers, our graph is possibly going to cross the x-axis at one of these 8 numbers there. So the way we're going to check here is by using the remainder theorem and substituting in any one of these values by trial and error, substituting these values into my function and seeing if that answer is equal to 0. Okay, so I'm going to start, as you see right here, I always start right here on my calculator. I'm not using the graphing one, I'm just using a regular scientific calculator. And I've already started by replacing all of these x values. Let me highlight them. These x values with a number from the list. I started with positive 1. And as you notice again on the right side right here, when I plug in positive 1 into those x values, 1 to the third plus 2 times 1 to the second minus 5 times that 1 value minus 6, I do not get a value of 0, I get negative 8. So this gives me a remainder of negative 8. So that means that this value is not going to be a 0 to an x-intercept to this function. So let's try negative 1 now. So let me just replace all of these values with negative 1. So that with a negative 1, negative 1, and this one with a negative 1. And I do get 0. So this tells me that negative 1 is a solution, that x equals negative 1 is a 0 solution, roots again, to f of x. So when I plug in negative 1, I get the value of 0. So what I'm going to do now, since I know that that is a solution, I'm going to use that solution to divide my polynomial using synthetic division. So I'm going to set up a synthetic division problem. I'm going to put negative 1, again, my 0 here. My coefficients to my polynomial are 1, 2, negative 5, and negative 6. And I'm going to follow the technique of synthetic division to divide this by the factor of x plus 1. So I bring down the 1 and I multiply, giving me negative 1, and I add, which will give me 1. Since I'm adding a positive negative value, that gives me 1. I multiply, that's negative 1. I add, that's negative 6. I multiply that negative 6 with negative 1, it gives me positive 6. And you see I do get that remainder of 0 like I'm supposed to, because again I checked it right here on the right on my calculator. So now, because of this quotient that I have right here is the polynomial 1x squared plus 1x minus 6, and I want to now find out what makes this equal to 0. So I'm doing essentially the exact same thing that we did yesterday, but the only difference is that I'm not providing, again, the 0, one of the rational zeros, and you have to find them yourself again from the list of possible rational zeros from the rational zero theorem. So right here we can then continue. Since we have a quadratic trinomial, we can factor this. Hopefully this is factorable. Okay. Oh, this should be a negative. This is not. That's going to be a negative. And we're going to look for the factors of 6. So 6 can be 1 times 6, 2 times 3. And since we want the middle number to be 1, whereas the first larger factor is positive and the smaller factor is being subtracted, that would have to be 3 and 2. So that tells me that x would have to equal to negative 3 and x would have to equal to positive 2. And if you look at the list, those numbers are also on the list because these numbers are rational. Those numbers are also on the list of possible rational values. Negative 3 is right here and positive 2 is right there. So when I put all this together, well, what's the solution? What are all the zeros to this function? They are the following. All the places that the graph is going to cross the x-axis will be at negative 1, at negative 3, and at positive 2. So there are your zeros. How cool is that? All right, let's move on to the next example that I have here. So let's practice this technique one more time. So on this example, again, since our leading coefficient is 1, the list of possible rational zeros is simply going to be all of the factors of our last number of our constant 20. So I don't have to do the same thing I did over here because the list again is going to look exactly like the same scenario as the previous one and from example 5a. So let me scoot back right here and let's look at this example. And from the smallest to largest, 1 is a factor of 20, 2, 4, 5, 10, and 20. All right, awesome. So now that we have this list, what we're going to do now, let me bring out my calculator. I already have my polynomial, x to the third plus 8x squared plus 11x minus 20. I'm going to pick a number from this list and see if it makes it equal to 0. So we're going to start by checking if, I'll start with positive 1. If I plug in 1, will this thing equal to 0? So let's plug in 1 into all of those parentheses there. And yes, lucky enough again, 1 automatically works. The first number from our list works. So since this does equal to 0, we know a couple things to be true. That x equals 1 is going to be an x-intercept. So we're crossing the x-axis at x equals 1 or 1, 0, which means that x minus 1 is a factor and x equals 1 is a solution to the equation of where this function is equal to 0 or a 0. We could just simply say that x equals 1 is a 0 to f of x. Now, the cool thing about knowing that this is again equal to 1, that 1 will make this entire thing equal to 0, is that I can use synthetic division now to find the quotient when dividing by x minus 1. So setting this up as 1, 8, 11, and negative 20, the quotient of this is going to be a quadratic trinomial that can then be factored or use the quadratic formula to figure out the remaining x-intercepts. So let's bring down the 1 here. So let's go through the technique, through the procedure of synthetic division. We start by bringing down the 1 and then we multiply that 1 with this 1 up there, which gives us 1, and we add these numbers. So that's going to give us 9. I now multiply this 9 with our 1, which is 9, and I now add that to 11, and I multiply that 20 with this 1, which will be positive 20, and that adds up with the negative 20 to give us again a remainder of 0, just like we were supposed to according to our calculation of plugging in 1 into our value there, okay? So far so good. Let me put this away. I don't need this anymore. And now we have x squared plus 9x plus 20 equals 0. Now, since this is a quadratic trinomial, hopefully this thing is factorable. We don't have to use the quadratic formula. And let's check. So we have x and x, plus and plus. Let's look for the factors of 20. Okay, and since we want the two numbers to add up to 9, that would have to be positive 4 and positive 5. So x equals negative 4, x equals negative 5, and there, we found our solutions, okay? Awesome, awesome, awesome. So along with the first one, x equals to 1, x will also equal to both negative 4 and negative 5. Which again, if you look at the list, how cool is that? Again, those numbers are on the list. Had I not decided to start with 1, I could have started off with negative 5 or negative 4 and then doing this whole procedure, synthetic division. That would give me another quadratic trinomial, and that would give me the other two. So had I started with negative 5 and put negative 5 in there instead of 1, doing the synthetic division would still give me a remainder of 0, but this quadratic will factor so that the answers to this quadratic would be 1 and negative 4. So I would end up with x plus 4 as a factor and x minus 1 as a factor, which again will give me those values there. So it all eventually again results in giving those values, which is really, really cool because as long as you find one of the three rational zeros, you'll ultimately end up finding the other two because of this synthetic division that creates this, like I said, this quadratic trinomial, which then can be factored. How cool is that? Okay, so let's now look at the next example. Let's turn the page and look at example C. So here, our leading coefficient is 1. So that means that the list of possible rational zeros is simply going to be the factors of our constant, which since 3 is a prime number will simply be a very short list, 1 and 3. So let's plug these values. Let's again pick one of those numbers and plug it into the x of our polynomial. And we'll just go in order. Let me start with positive 1. If I plug in positive 1 into all the values of x, that doesn't work because I end up with negative 16, not 0. So let's try negative 1. Negative 1 doesn't work either because that gives me negative 8. So let's try positive 3. That didn't work either. That gives you 120. So by a process of elimination, it would have to be negative 3. Yep, negative 3 is the only one here that makes this thing equal to 0. So that's the only rational value that we have. So with negative 3 being the only one, that's the only option that we have. So, which is kind of funny because that would mean that the other values are not going to be rational. They're going to have to be irrational or maybe even complex. So let's go through the synthetic division and see what our quadratic, I forgot the name of quadratic, is going to look like. So we bring down the 1, multiply that, that's going to add negative 3, this will be 4, negative 12, negative 1, positive 3, and 0. So yeah, this is definitely not factorable. Okay, there's no way we're going to be able to break this up into factors because of that constant. The value of 1, there's only one way to get 1. That's 1 times 1. And that's not going to give us this 4 that we need right here in the middle. So factorization is definitely out the question. So this technique is not going to work. So I'm going to erase it. You could probably just scratch it out if you already copied this down. So that is definitely not going to work. So what other option do we have? Well, the only other option is to use the quadratic formula to figure out what those values are. So our value of A, let me move this down a little bit so I could give myself a little bit more space. Our values of A, B, and C come again from our quotient. This would be A, B, and C, and we're going to plug it again. We're going to plug them into our quadratic formula. So negative 1 or negative B is our value of 4, so negative or positive 4 plus or minus our 4 to the second power minus 4 times A times negative C, or negative 1, which is our C value, and divided by 2 times our value of a, which again is 1. So let's simplify this. Start by simplifying this right there. The negative of positive 4 is negative 4. Now let's focus on the radicand. What is our radicand going to equal to? Right here. Highlighted it instead. Okay, our radicand. Let's see what that radicand is going to equal. So let's, oh, I shouldn't have done that. That doesn't matter. Okay, let me just hit enter to get a new line. So let's do 4 to the second power minus 4 times 1 multiplied with negative 1, and that equals a total of 20. So we have the square root of 20. And then 2 times 1, well, that's equal to 2. So there. So here are the two irrational values because the square root of 20, let me just write that in, the square root of 20 is equal to a decimal value. So you do not want to write that decimal value. You want to write it like this. You could possibly simplify this because I'm seeing again that 20 does have a perfect square. So let's do that for this example. And let's write 20 as the product of 4 times 5. That gives it 20. And you'll notice again, I could have done other numbers that give you 20, but I use this one because I know what the square root of 4 is. The square root of 4 is 2. So if I write that as the square root of 4 as 2, I end up with 2 times the square root of 5 divided by 2. And now, both of these values are divisible by 2. Awesome. So I can divide this and this by 2, which reduces this to negative 2, not 4, negative 2 plus or minus 1 times the square root of 5. And of course, over 1 because I'm reducing this also by 2. So my denominator will be over 1. So here are my two irrational. So this is the reason why I couldn't find any of the other numbers, why any of the other numbers didn't work. The only number that worked was negative 3 because negative 3 is the only rational solution. So these two numbers, remaining two numbers, negative 2 plus the square root of 5 and negative 2 minus the square root of 5, those are irrational values. So that's the reason why I couldn't find, and only one of those numbers worked. So our answer will be this. And here are the three places that the graph is going to cross the x-axis. Now, since I have a plus and a minus, I could actually combine these. And instead of writing them separately, I can write them as one value right there. And just simply putting a minus sign underneath there, that's both positive and negative, the square root of 5. So that notation is telling me that I have negative 2 and I'm adding and then also subtracting the square root of 5. So instead of separating like I did earlier, I could just write it like that. So here are your x-intercepts, where the graph is going to cross the x-axis. Okay, so now let's look at this example. Again, since the limiting coefficient is 1, I just have to worry about the number 2. So our list of possible rational zeros is essentially just the factors of 2, which again, since 2 is a prime number, is going to be a very short list of just 1 and 2. So let's again bring out our calculator and let's plug in 1, 2, negative 1, negative 2, and let's see which one gives me 0. Let's start off with 1. And I do not get 0. So let's do negative 1. That doesn't give me 0. So let's try positive 2. And that does give me 0, okay? So x equals 2 is one of our solutions. So let's use that solution and using synthetic division, divide that by this factor, this x-intercept, to figure out what the quadratic is going to look like. So we have 1, 3, 6, this will be 1, 2, and then 0. And as you can clearly see, x squared plus 3x plus 1, try to get that equal to 0, that's not going to work. This is not factorable. There's no way we could break again 1 into any type of possible way that gives us again this middle value of 3. So factorization again is not going to work. So we have to use again the quadratic formula. So again, both of these numbers were eliminated, and the only one that we found that worked, or not the only one that we found, but because we only checked this one, and I then continued. So it doesn't look like -2 is going to be a solution, because if -2 was a solution, then this would have to be factorable, and one of these factors would have to give me the answer of x equal to -2. So it doesn't seem that that's going to be the case. So we have to use our quadratic formula. So we want, let me fill in first all of this stuff, and then we'll write in the numbers. So the values of A, B, and C are 1, 3, and 1 respectively. And we start by getting the negative of B, so 3 goes there. B squared, so 3 goes there. Minus 4 times AC, so A and C are both 1s. And again, divided by 2 times A. All right, cool. So now, let's simplify this expression. So we have -3 plus and minus for the radicand. Probably should have done that off camera. Let me just do it here. Our radicand 3 squared minus 4 times 1 times 1. That equals to 5. Now 2 times 1 gives us 2. Let me move this down. Kind of wrote it too close to that last one. And there's our answer. We can't simplify this any further. 5 again is a prime number, so we can't do what we did on the other example. So there's our solution. So x equals to -3 plus and minus the square root of 5 divided by 2. Along, of course, with the one rational solution of x equals 2. So there are your 3 x-intercepts. How cool is that? This one should be example E, so make that correction on your notes. And let's look at example 5E. So again, since our leading coefficient is 1, the list of possible rational zeros here will be the factors of 26. So let me write those very quickly. No, 3 is not a factor of 26. 26 divided by 3 ends up equaling to a decimal value, so that's not it. 4 isn't, 5 isn't, 6 obviously isn't. The next one would have to be 13, and then 26. Okay, so now let's check which of those numbers is going to be a 0. Okay, so out of these 8 numbers, after some trial and error, I tried 1, I tried -1, those didn't work. I tried -2, that didn't work either. And then I finally tried +2, and that's the one that made this polynomial equal to 0. So that's one of our solutions. Sorry we went through the process just to save us some time. And by trial and error, I finally found the one x-intercept, the one x rational, let me be specific, the one rational x-intercept of 2. So let's now use that value and use synthetic division to figure out what the 26, what the quadratic will look like. So bring down the 1, this is 2, this is 6, 12, 13, 26, and then of course 0. So let's look at this. Let's see if factorization will work again, because it didn't work on the last 2 examples. Maybe we'll get lucky, and factorization will work now on this example. So we have the factors of x which add them both because they're both positive, and the factors of 13. Well, 13 is a prime number, and 1 and 13 are the only values that give me, again, 13. And that combination doesn't work because both being positive, or even if they were both one positive, one negative, they are not going to combine to give you the value of 6. So unfortunately, factorization is not going to work here. So this was all done in vain. So that means that we have to use, unfortunately, yet again, the quadratic formula. Okay, so here I have my quadratic formula. The values of A, B, and C are 1, 6, and 13. So let's plug those numbers in the respective places. And we end up with negative 6 plus or minus, let's simplify this right here. And then we end up with 2 in the bottom. So let's bring out my calculator again, and let's figure out what the discriminant equals. So we have 6 squared, like I said, minus 4, 1, and then 13. And, look at that. We end up with a negative 16. How odd is that? So that means that none of the other values, the solution to this after the quadratic formula is not going to, again, be on this. It's not even going to be a rational value. It's going to be a complex number. So when we use the quadratic formula, that automatically eliminates any possible way that any of the other numbers, other than 2, of course, and the ones that we eliminated, are going to be possible rational zeros because factorization doesn't work. So we already knew that our solutions were not going to be 13, neither positive or negative 13 nor positive negative 26. But it's not even going to be a real number. It's going to be a complex number because the square root of negative 16 is equal to an imaginary value. So we have negative 6 plus and minus the square root of positive 16 is 4. So negative 16 will simply be 4i. And then dividing it by 2, we get our solution. So negative 6 divided by 2 is negative 3. 4 divided by 2 is 2. So there. So x equals not only to negative 3 plus or minus 2i, but also the one rational solution that we found of positive 2. So there are your x-intercepts, okay? And this right here is a complex intercept. So if you were to graph this, you would not see that the graph is going to cross the x-axis other than the value of 2, which is really, really neat. Okay, so look at this. Look, I have the function x to the third power plus 4x squared plus x minus 26 graphed right there. And notice that we crossed the x-axis at positive 2. Again, the value that we found, again, using our remainder and factor theorem there. But look at the graph. Look how the graph does not intersect the x-axis anywhere else. Notice that it goes up and it doesn't look to be going down. And I know that for a fact if we apply the leading coefficient test. Because of this leading term, I know that this end is going to be pointing upwards. Let me transcribe it on my paper. I know that the right end is going to be pointing upwards because this number is positive. And since this number is an odd value, I know that the left side is going to be pointing downwards. So that's exactly what I see there. Because of this, I know that this graph is not going to move downwards anymore. That right end, since it's pointing up, is going to continue pointing up and never turn around. So the curvature is happening again right here in between negative and positive 5, where it goes up and goes down and goes back up. And we only cross the x-axis at positive 2. How cool is that? Because it correlates exactly to the concept that since we ended up with only one rational zero and two imaginary complex zeros solutions, that the graph only crosses the x-axis at one location. So very, very neat again on that example that we end up with these complex solutions. Finally, the last example I want to go over is, well, it's labeled as E, but it should be F. So fix that for me on your notes. That should be example F. And we have f of x equals x cubed minus 9x squared. So that should also be squared plus 24x plus 34. So let's look at the list of possible rational zeros. is simply going to be the list of factors of this last number, since this number right here is 1. So 2, not 3, not 4, not 5. Then 17, and then of course itself, which would be 34. Okay. So let's see, let's try some values. Now off camera, I plugged in 1, I plugged in 2, and that didn't work. Then I tried -1, and I found that that value does in fact equal to 0. I tried -2 first also, but that didn't make it equal to 0. And the one that works is going to be -1. So as you see right here, I have that this again, plugging in -1 makes it equal to 0. And off camera, I did try +1 and -2, and those didn't work. So I can scratch this out, and I can scratch that one out. So using that x equals 1, let's now use synthetic division and get our quadratic. So they move this away. So we have 1, -8, negative. Hold on, I did this wrong. Let me back up. -1. I said -1, and I put +1 right there. So let me fix that. Okay, so -1. So that will give us -1, which changes this to -10. So a +10, which is 34, and -34, that does in fact give us 0, because I wasn't getting 0 because I messed up and put the wrong number. So x equals -1. Now, this again is not going to be factorable. I can kind of already see it. We have x squared minus 10x plus 34, and we want to get the value of 10. We already have the factors of 34. We listed them up right here of 1 and 34, and then 2 and 17. No combination of those two sets with predetermining the signs having to be both negative are going to give me a value of 10. Neither 1 nor 34 nor 2 and 17. So this whole procedure of trying to use factorization was all in vain because none of this works. So let me erase this. No, I don't have to erase it. Let me just move it out of the way. Make it a little bit smaller. And we can then apply the quadratic formula instead. We have no choice but to use that one. Okay, so here I have my template for the quadratic formula. I'm going to plug in now the corresponding values. So a -10 goes in there, in there. The value of A goes in this parentheses here. The value of C goes in the parentheses next to that. And in the bottom, the 2 gets multiplied with the value of A, which again is 1. So let's simplify the outside parts, both in numerator and denominator. And let me get our calculator so we can identify what the discriminant equals. So we have a -10 to the second power. Oh, I meant to write negative. Not that it matters. It's still going to be 100. As you see, both positive or negative, I still get 100 there. Now minus 4 times the value of 1 times the value of 34, I get a -36. So with this being a negative value, we're going to end up with the same type of scenario as the previous example where, well, this one happens to be, again, a perfect square. If this wasn't a perfect square, I would just write the I in front of that so I can get rid of the I. And this would be our answer. 10 plus or minus I times the square root of 36. So I would simply get rid of the I, make it into, I'm sorry, the negative sign inside the square root by making it into an I. Now let's check if 36 is a perfect square. And yep, it is. The square root, not that one. The square root of 36 is a perfect square. It's equal to 6. If it was a decimal value, then I wouldn't simplify it. But since it does equal to 6, let's write that value instead. So let's see. Come on. Let me move this out of the way here. There we go. So we're going to have 10 plus or minus 6i divided by 2, which reduces to 5 and 3, along with our other solution of -1. Here are the solutions and my x-intercepts, aka my zeros. So here are the zeros to this polynomial function. Well, that concludes the second part to 5.5. I hope this video was helpful and clear and concise. I appreciate you watching, and like always, I hope you have a great day. Goodbye.